Okay, good. So the first speaker of our morning session is Professor Dongmin from Seoul National University, and he's going to talk to us about torus knots and Virasoro minimum models. Please go ahead.
Okay, so good morning. So first, I'd like to thank for organizer, especially Rak-Kyeong and Masaito for giving me the chance to talk here. And I also thank you all for coming to my talk, although it is very early in the morning in my standard. Yes. So I'm going to talk about torus knot and the Virasoro minimum model. This is based on some work in progress with my PhD students, Hee-Jun Son and Byung-Yun Park. And so I think this workshop is a little more math-oriented workshop. So let me start with some math. So my introduction starts from some curious observation by Jagier and Lawrence in the last century. So in this paper, they found that interesting relation that some non-hyperbolic three manifold. Some simplest example considered in this paper is this Poincare homology sphere, which can be given by such this templing tensor description. And what they found is that and they consider some quantum invariant called the WLT invariant and do some multiplication, and it turns out that this partition function this WLT invariant can be turned into some modular form. Actually, it will be some just vacuum character over the rational VOA, and they found that this one. So and then they found that this has a modular form of degree 3.5. And here's the and it turns out that this is close another one more step. It will relate to some vacuum character of the rational VOA. So here, rational VOA is roughly is a short for the rational vertex operator algebra, and roughly it is a symmetry of the chiral part of the rational component field series. So some of you are very familiar with this dense surgery representation, but I assume that most of you are not familiar with. So I'm going to review some basics of the three manifolds, and I will introduce some notation, and which will be used throughout my paper, throughout my talks. So we are considering the knot and links inside the three spheres, and which is given by this knot. And this is so-called the PGA knot, which is sometimes denoted by the 4-1 knot, because there is a 4 crossing, and this is the simplest knot among 4 crossings. And this is pivot knot, and the same reason this is called the pivot knot. And the main hero of my talk is the so-called PQ torus knot, which is labeled by 2 coprime P and Q, and these are the PQ torus knot. So you can easily generalize to arbitrary PQ from these drawings. So torus P and Q is you can easily see that so we are considering three sphere, we are considering solid torus, and this knot is given by the wrapping some PQ cycle of this boundary of a solid torus. So this is the meaning. So you can see that this is a 1,0 cycle, and this is meaning the 2,3 cycle, and yeah. So this is really denoted by the calligraphy and PQ. And we also consider some link complement from three sphere, which is given by, which we will denote by this one. We are removing the tubular neighbor of the knot or link of this three sphere. So if we are considering PGA knot complement, and roughly this is a tubular neighborhood of PGA knot, and we are removing this tubular neighborhood from three spheres, and we will get a knot complement. Then we also consider dense surgery. We are gluing back. Here is a knot complement. We are removing the tubular neighborhood, and we are gluing back this tubular neighborhood with the solid torus with some non-trivial way, which are labeled by the P and Q. So knot complement has a torus boundary. Torus boundary has and one cycle is generated by so-called meridian and the longitudinal. longitude. And we are gluing this in the gluing story torus. We are gluing some PQ cycle of this boundary torus, boundary cycle to some shrinkable cycle of story torus. Then this will give some 3 manifold, which I will denote by in this notation. These are labeled by P and Q. So sometimes I will also draw in this notation. It means that we are considering PK knot and we are doing the density along the PQ cycles. That's the meaning of this manifold. This is closed manifold without torus boundary. So now you can see the meaning of this manifold, and this is so-called homological spheres. And they found that there's very systematic way to compute the duality invariant, Wilson taken to drive invariant, and they do some manipulation which I cannot fully understand. Then they get some modular form. But I am very surprised that they missed the fact that this modular form is actually become the vacuum character of the rational CFT up to some trivial dedicated eta function. So multiplication of dedicated. If you divide by dedicated eta function 3, which will kill this degree of the modular form, then we will get a degree 0 modular form. It's a modular function, and this is actually become a vacuum character of the T2 level 1 Bestman-Witten model, which is one of the rational component field theories. And this observation was further generalized by mainly by the Kazuhiro Hikami. And one interesting example is when we are considering torus knot, which I mentioned, is labeled by P and Q. And they consider some quantum knot invariant, which is called Kashaev invariant. And they consider almost same thing what the Donjage did, and they found that the resulting shear is a vacuum character of the Virasoro minimum model, which are labeled by also P and Q. So Virasoro minimum models is some, in a sense, a very most well-known example of the rational component field theory, which are labeled by 2 co-primes. And these are also labeled 2 co-primes, and these are labeled co-primes. So they are natural map, and they found that not only just the labeling, but they found that some invariant of this one is actually same as some basic invariant of this minimal model. So then the natural question is that this observation makes sense that if you choose very nice choice of the 3 manifold, mostly non-hyperbolic cases, seems that we can assign some corresponding rational VOAs. So we may ask that which 3 manifold will allow this kind of map, and how does it work? How can we assign some rational VOA from the 3 manifold? That's the most natural question, I guess. So here is the outline of my talk. So I just explained this curious observation by mathematician. Basically, some nice choice of 3 manifold, and we can get a rational VOA. So in this talk, I'm trying to convince you that this map is very natural in terms of physics, because so there is a very well-known map from the 3 manifold to 3D n equal to k theory, which is called the 3D correspondence, which is developed by these people. And so I will first briefly explain the 3D correspondence, which roughly says that if we have a 3 manifold, then we can assign a 3-dimensional gauge theories. And more recently, we found that some certain nice choice of 3D n equal to k theory, then we can assign some 3-dimensional topological field theories. Topological field theory means that topological field theory whose mathematical structures are described by the so-called modular tensor category. And then it is well known that in topological field theory, they have some allowed gapless edge mode, which are described as rational VOA. This is how we explain that these are related. So combining these 2 correspondence, then if we collaboratively choose some certain manifold, then we can naturally assign from this map, we can assign some 3D TQFT determined by this 3 manifold, and also some rational VOA determined by this 3 manifold. So here, main example of my talk is that torus knot complement cases. So we will give so each step is very well understood. So I will just apply this all well-developed technique to this torus knot, and it turns out that naturally I get some Virasoro minimum model on this map. This is the main result. So rest of my talk, I will focus on explain these two correspondence. Any questions so far? Yeah.
At the beginning page, this Pommery sphere is
Yeah.
like a big one.
It is a closed manifold. It's without any boundary. Yeah, and
I mean, it has 4 components.
for convert, and we are do the damping along this. So here I give nice question. So it means that I have damping. So, yeah. So if this rotation is close. Sorry. Yeah. Any other question? Yeah. So let me briefly explain the 3D circular component, which is basically assigning the 3D n equal to k theory from the 3 manifold, and 3 manifold are given by some knot complement, or so we can consider some damped knot component, which is closed manifold. And then we will assign the 3D gauge theory, which is labeled by Tm. And the motivation comes from some M theory. M theory, we know that there is some extended object called the M5 brain, and its world volume theory is known to be described by the exotic 6-dimensional some supercomponent field theory, which we will usually call the 60 A1, 0 theories. And we are doing some twist compactation over this 62,0 theory along the internal 3 manifold with some partial topology twisting along this 3 manifold. Then after dimensional reduction, we will expect to get some 3D n equal to k theory. The partially topology twisting preserve a cut of the supersymmetry, and the resulting system has only n equal to supersymmetry in terms of 3D n equal to superalgebra. And then region theory, we generically expect that this will theory become 3D n equal to theory on the non-compact direction, 3-dimensional space-time, determined by the whole topological data of the 3 manifold. So I will consider this. So I will denote this theory as Tm. And minor technical comment is that the Tm theory in my talk is not actually their subtlety. So in a sense that this theory only is known to see the only irreducible component of this Tm. For example, if we are considering some beta vacuum of this so-called beta vacuum of this gauge theory, it does not see the full SL2 flat connection, only see some adjoint irreducible flat connections on the 3 manifold. So, but we are considering only T irreducible, but to avoid clot, I will just denote the Tm. And then I will explain how to construct this 3 manifold 3D theory from some basic topological data of 3 manifold. So to explain this basic topological data, which is basically so-called Neumann-Jaeger matrices, I will need some math. I need to also introduce some math, which is ideal triangulation of knot complement, which is firstly introduced by Thurston, to prove that some knot complement have hyperbolic structures. So the idea is that we are topologically decomposed into 3 manifold knot complement, which is something like a knot complement, into some basic building blocks so-called ideal triangulation. So ideal tetrahedra. So for example, that one most famous example of this ideal triangulation is so-called pigay knot. It's known to can be glued by 2 tetrahedra with some identification of this one. Although this is very difficult to imagine, but yeah, so Thurston proved that. Yeah, I don't know how to prove, but actually show that this is actually the topological equivalent. And then this decomposition using the hyperbolic structure of this tetrahedral, he can construct the hyperbolic structure of this knot complement. And so generally, so if we have some knot complement 3 manifold, we can decompose it into ideal tetrahedra, and this green data will determine this 3 manifold topology of 3 manifold. And another method we need is that it's also very non-trivial result is that Neumann and Jagier found that this gluing data has very nice simplet structures. And in gluing equation, gluing data has some nice simplet structure. And then we can assign some simplet matrices given by this SP2RZ matrices. Here's A, B, C is the R times R block matrices, and this R is the number of tetrahedra. So I'm not going into detail, but there is a certain way to construct this ABCD matrices from the given ideal tetrahedron. So figure in that cases, this can be glued by this way. Then I'm skipping every details, but we can obtain this SP POZ matrices from some combinatorial way. So in this way, this information contains some gluing data of this ideal tetrahedron. So this matrix actually depends on the 3-manifold, of course, and also depend on the ideal triangulation. For given 3-manifold, there's infinitely many ways of the triangulating this ideal tetrahedron, and also some secret choice of assigning some so-called H parameters and all the other informations. Yeah. So in figure in that case, I'm using this matrix, but this is not unique form, but there could be some equivalent, some another expression for ABCD matrices. Anyway, so for given choices, there is a very well-known way to combinatorial way to construct this ABCD matrices. And this is a basic information we need for constructing 3D gauge theory associated 3D 3-manifold. And let me also explain the basic construction of a 3D n equal to gauge theory, which is labeled by the choice of the R times R symmetry matrices, integer value symmetry matrix K, which is called the Chern-Simons level, and some superpotential deformations. So generally, 3D n equal to gauge theories are determined by the gauge group and the matters field and the Chern-Simons level and superpotential. But for our purpose, we'll consider following class. Only is a certain nice class, which are labeled by only the simple data K, which is R times R symmetric integer value matrices, and some superpotential deformations. This theory is in physics language. This theory is given by the U1 to the R Chern-Simons net theory. Chern-Simons level is given by this one, coupled to R chiral multiplet of charge matrix is given by the identity matrix. It means the first chiral is charged on the only first U1, and the second one is charged only on the second U1, this one. And with some superpotential, which is denoted by OI. Here is some integer valued matrices, and these superpotentials are labeled by the magnetic charge and electric charge, and they are subjected to some concrete mathematical condition to be gauge invariant and to be the scalar operator. Anyway, so for given K, we can construct some gauge invariant and hypothesis local operator labeled by M and E if M and E satisfy certain concrete relations, which is gauge invariance condition. And for given K, then there is a very concrete relation which M and E should satisfy. And also further, we also need to require that this superpotential should be relevant. Then there's only finite many choice of the M and E's are given for given K. So in a sense that this theory is almost wholly determined by this simple data of K matrices. Then this theory, this construction says that for given 3-manifold, we can construct this Neumann-Jaeger data, which is A, B, C, D matrices. And then they assign us corresponding 3D n equal to gauge theory, which is labeled by the K Chern-Simons level K, which is determined by this Neumann-Jaeger matrix in this way, P inverse A. And the superpotentials also can be determined by some gluing equations and the internal edges. So from this data, there is a natural way to construct the field theory. And what non-trivial thing is that this construction does not depend on the other information other than the three manifold. As I mentioned, this Neumann-Jaeger data depend on some ideal triangulation and the choice of some other choices. But actually, this theory itself looks all different, but the different choice will always give the same 3D theory if the three manifold are the same. So TM in this construction, beautiful aspect of this construction is that TM only depend on the topology of three manifold up to some IR dualities. So these are the well-known construction. And this construction also can be generalized to the more closed manifold by incorporating damping in 3D series correspondence. And and then I will skip the details anyway. So if there is if given damping, then there is a way to construct this 3D n equal to k theory. And another beautiful aspect of this construction is that this construction is, although we haven't proved it, but seems to be invariant under the Calabi move. So three manifold, closed three manifold allow several different density description, and each density description give a different field theory construction, but they all related by some IR dualities. So P is damping coefficient. So as I mentioned, and so to construct the three manifold, we need this information, and the P means that Q equal 1. It is so it is not that all the three manifold can be constructed in this way. So all the closed manifold, the corresponding theory can be constructed in this way. So in this way, so for given three manifold, either it is a not complement or the closed manifold, there is very system that we can assign some 3D n equal to k theory. Although the form of the 3D n equal to k theory are not unique, but they are all different. K theories are known to be brought to the same IR physics. So in a sense, they are all the same. And then now I explained how to construct from the 3D n equal to k theories to the 3D TKFT and some rational VA. This is possible only for some nice choice of 3D n equal to k theory. If you give a generic 3D n equal to k theory, generally it does not work. But if you choose very cleverly Chern-Simons level, then there is a way to construct the 3D TKFT and the rational VA. So let me explain generally how to construct the 3D TKFTs, topological field theories, from the 3D n equal to k theories. UV data is given by 3D n equal to k theories, which is given by the gauge group and Chern-Simons level and the spot potential. And under the normalization group, and depending on this theory have a mass gap or not, this IR page is schematic given in two categories. When there is no mass gap, then this theory genetically will prove to 3D n equal to supercomponent field theories. And if this theory has a mass gap, then this will theory prove to the three-dimensional unitary TKFTs, mass gap cases. And this is one way to construct the TKFT. So if we collaborate through the Chern-Simons level and the gauge group and the spot potential, then this theory will flow to the unitary TKFT. And this is one way to construct TKFT. But if you choose generic 3D n equal to k theory, usually there is always a second order phase transition, and we will get this kind of CFT. But if we choose very cleverly, then we can sometimes get this unitary TKFT. This is one way to construct the TKFT. Another way to construct TKFT is that when this theory has some enhanced supersymmetry. This is generically n equal to CFT, but if we very cleverly choose this Chern-Simons gauge theory, then sometimes it has supersymmetric enhancement miraculously, and this has allowed 3D n equal to supercomponent field theories with some non-trivial supersymmetric enhancement in IR theories. When there is n equal to supersymmetric cases, we can do the so-called topological twisting to get a topological field theory. So in this example, we can do some topological twisting that we expect to get some topological field theory. But when the 3D unequal to CFT is has either Coulomb or Higgs branches, and the twist theory is not the genuine TQFT, it's the extended TQFT. So we are only focusing on the genuine TQFT, which is described by the semi-simple and the finite modular tensor category. Then we need to further require that the rank 0 conditions. Rank 0 means that the n equal 2, n equal 4 CFT doesn't have either Coulomb or Higgs branches. Then in these cases, after topology twisting, we will get some non-unitary TQFTs. So topology twisting always break unitarity, and this will get a non-unitary TQFT. So these are the two ways to construct the TQFT. So genetic choice of a tensile level never work, but if we choose very cleverly, choose a tensile level, then we will have a chance to get out this TQFT from this non-trivial some dynamical mechanism.
If we start from, say, the genetic and equal probability theories.
Yeah.
And then the particle twisting.
Yeah.
Is it known that what kind of probability theories we are obtaining there?
That case is if we are considering the general n equal 4 theory, then the resulting CFT always have a Coulomb branch or either Higgs branches. And then if there is a Coulomb or Higgs branches, after topology twisting, it does not give the, in a sense, genuine TQFT, in a sense that this is described by the unitary finite semi-simple modular tensor category, but some TQFT which are described by some extended TQFT, whose structure is not well known so far. So people are...
If you just particle twisting,
yeah,
does it mean that the result theory is some kind of particle
yeah, some kind of topology twisting, extended TQFT, not the TQFT in a sense of the RTI and the Seeger, which is identifying some nice mathematical action, which is described by the unitary modular tensor category structure. It's some extended, non-semi-simple, non-finite, even non-finite TQFTs, which we do not have, we still do not have a full control over the TQFT. But in this case, we have full mathematical control. This is mathematically well-defined, and even mathematicians try to classify all this mathematical structure. Yeah, of course, non-semi-simple TQFT is also very interesting because it is new direction, and people are trying to extend the conventional notion of TQFT. But in my case, I'm focusing on the genuine TQFT, and which support the rational buoy at the boundary.
Any part twist just metric case, can you do anything? Like is there Rak-Kyeong any part P where you can twist?
And for 3 cases.
Any part twist plus symmetry.
And so
For 3.
and for 3 we cannot do any topology twisting. Although there is the SO3 asymmetry, but every topology twisting there's no 3D distributor. So charge is types on the 3 under the asymmetry, but under the SO3 rotation symmetry it is types on the 2. Then So, and for 3 cases, we cannot do any topology twisting. So rank 0 TQFT is so recently found exotic and the simplest class of n equals 2 CFT. Rank 0 means that no Higgs branch and Coulomb branch. So as Jemo asked, that if we start from general n equals 4 case theory, then we usually get the non-rank 0 CFT. So in the higher dimension, it is believed that although it is not proven, and this is still controversial, but so far, some people believe that there's no rank 0 CFT in the higher dimension with a supercharge in the higher dimension. The simplest and the basic example of this rank 0 CFT is so-called the minimal rank 0 CFT, and which is personally found by me and Masaito. And this theory has only UV discussion which have only manifest 3D n equal 2 gauge theory. And the UV gauge theory is very simple. This is given by this K matrix is 1/1 matrix with tensile level 2. This means without any superpotential. This means that U1 tensile level 3 half coupled to single chiral. in a sense, this is the most simplest tensile method theory we can consider in 3D n equal to k theory. And the UV k theory, this theory has a 3D n equal to spot symmetry and the U1 topological symmetry, which is comes from the U1 k symmetry. And there's also U1 R symmetry, of course. This is a symmetry, which is included in the 3D n equal to SUJI algebra. And in this paper, we argue that in the IR, this theory has some non-trivial spot symmetry enhancement and the flow to the n equal 4 length, n equal 4 CFT, and we found that there's no Coulomb Higgs branches, and so this becomes the 3D n equal to rank 0 CFT. So in this argument with various non-trivial some evidence, we argue that this theory will flow to the under the RG has a spot symmetry enhancement and it flow to the n equal 4. Under the n equal 4, under the RG, then the U1 R symmetry and the U1 topological symmetries are enhanced to the SO4 R symmetry of 3D n equal 4 symmetry. And there is a very non-trivial consistency check of this localizing technique, and we are now strongly believe that this enhancement really occurs. And this is so this is why this length 0 CFT are found only very recently. This length 0 CFT only can be considered by only this kind of non-trivial symmetry enhancement method. And the nice aspect of this length 0 CFT for our purpose is that this will give a non-unitary genuine TKFT after A, B topology twisting. So genuine means that these mathematical structures are determined by some very rigid mathematical structure called the modular tensor category, a finite semi-simple tensor category. These days, people are extending this notion of the modular tensor category to non-finite and non-semi-simple and some exotic non-example, but the original definition of modular tensor category include the finite and semi-simplicities. And another nice thing about this length 0 CFT is that it supports non-unitary rational VOA at the boundary. So for unitary cases, it is very well known that this unitary kept case, such as a fractional transformer system, allows some capitalist edge mode, which are described by the physics of this rational VOAs are described by the so-called rational. And the notion of the unitary rational VOA can be easily generalized, mathematically generalized to the non-unitary rational VOA. And the notion of the unitary TKFT, unitary modular tensor category also can be easily generalized to the notion of the non-unitary topological field theory. But the one missing point was that we didn't know that how to realize this non-unitary bulk theory from the quantum field theory aspect. So recent development, we gave us some field theoretic, quantum field theoretic realization of this non-unitary TKFT, and this non-unitary topological theory also allow the support the non-unitary rational boundary at the boundary. So this is very natural mathematical. In terms of mathematics, it's very natural generalization of this setup to the non-unitary cases. But the non-trivial thing is that this bulk theory in field theory size, this is given by the quantum field theory with the mass gap, but this theory is described more exotic way. So there is a spot symmetric, and there is also stupid to the topology twisting. So these are only the mechanism we can have a chance to get some rational VOA from the 3D n equal to k theory. Either has a mass gap or have a non-trivial switch enhancement and to the topology twisting. These are the only mechanism we can get some rational VOA, can be unitary or non-unitary from the 3D n equal to k series. And the more strong conjecture is that it cannot be proven, but we believe that every non-unitary TKFT and every non-unitary rational compound field theory can be realized in this way. This is a very strong statement. Cannot be proven, but we believe that that's also. I hope that is also true. Yeah. So Yeah. So one technical thing is that in general, the tracking the neural net flow is very difficult. But for supersymmetric cases, thanks to the so-called supersymmetric localization, which is a basic computer RG invariant Bifest constant function, we can keep track of the neural net group flow for the supersymmetric n equal to k theory. And using this technique, we can check that for given n equal to k theory, we flow to the mass gap or not, or something like that. For example, if we compute the spot component index equal to spot component index, which comes in local spectrum of this theory, and if we become spot component filter theory become trivially 1, it means that there is no local operator other than the identity operator. It is strong signal that this theory has developed a mass gap. In this way, we can check that whether this UVK theory will flow to which category. And so, and then using the combining this the bulk boundary correspond upon a very clever choice of boundary condition, we can support some rational Boyer from this one. This is a basic idea of how to construct the rational Boyer from the A series. And more expressly, we can compute some quantity called the basic quantity of rational Boyer called the vacuum characters. Vacuum characters of this rational Boyer is roughly the algebra, and there's a representation, and we are taking some characters, and this is called vacuum characters. And this can be computed localization, so-called half-index computation, which is basically computing the disk times S1 with a suitable boundary condition, and we can reproduce the vacuum character of this rational Boyer. And this rational Boyer cases, this vacuum character is known to form some vector valued modular form, and this becomes some modular function under the some congruent subgroup of SL2G. So this character has very nice property, modular property.
Around it.
Yeah, loop around, yeah. So we are inserting there is some corresponding loop operator, then we can also compute the non-vacuum characters. Yeah, also. So let me give some concrete example. T minimal for the cases. This is in the RG, this will flow to the rank 0 CFT T minimum and A twisting, and we can compute the various quantity, and it turns out this is so-called equivalent to the Liang TQFT, which is the simplest non-unitary TQFT, and by bulk boundary condition is for some Liang Boyer of the so-called Liang Boyer at the boundary. And at the level of the characters, we can check that actually using this description, we can compute this half index using localizing formula, and then we can do some A twisting limit. Then we can get some vacuum character of the Liang CFT, which can be written in this form. And the Liang vacuum character is known to be written in this form for a long time, and this is so-called the Namson formula. And many RCF character is known to be written in such a Namson formula.
Yeah. So this F index apparently appears if we consider, say, the localization. And then if we have this, say, the spot component index, then if we consider factorization of the spot component index, then the quantity appears. Now then you can reverse this thing so that we have this half index, then another half index, and they combine it together to give rise something. Have you ever tried that, or what kind of?
This half index and this holomorphic block, so-called holomorphic block in factorization.
What is it?
Holomorphic block.
Okay.
It's this time there's one pattern function appearing in the factorization. They are also called the pattern function of this time there's one, but slightly different. Yeah, because the defined half index, we should choose some boundary condition.
Okay.
And I think that the holomorphic block boundary condition and our boundary condition is somewhat different. So we don't know the direct relation between the half index and the holomorphic block So using this one, we cannot reconstruct the Stockholm index, unlike half the Prolepula. We combine them, we can construct the Stockholm index. But I never tried to combine this one to get some Stockholm index. But I'm not sure whether it works. Yeah, it's different properties. Although they share the very many same property, and the people believe that this Hopper index and this whole plots are analyzed by same difference operators.
Okay.
Yeah, but yeah, somehow slightly different. And you can tell like in the model, this analysis more cases, and we are considering this K matrix given by this one, and giving focal deformation in this one, and we analyze field theory, and we found that in this paper, we found that this theory flow to the length zero CFT. And then we can compute the half index, and then we get this formula, the lump-sum-like formula, and then after the Q expansion of this expression, we found that this is nothing but the vacuum character of the diversity minimum, some diversity minimum. And so this way we can give the new expression for this lump-sum, new lump-sum expression for this vacuum character of the diversity minimum. So one thing is that this is not the same as the lump-sum formula, but slightly modified because there is a minus sign. And so nevertheless, it will give us some correct vacuum character of this the rational OOA. So in this way, we can, in this analysis, we can give infinitely many new expressions for the known characters of the rational view. So now we combine the two correspondence, then we will get some, if we properly choose the three manifold, and using that map from three manifold to three n gauge and three n gauge, three QFT, and we will get some three manifold from three manifold to three QFT and the rational volume. For that, we need to understand some IR case of the class R. To get some topological field theory, we need to analyze that IR case of the 3D TM theory, which is for closed manifold cases, it is done by this people. And so for general closed hyperbolic manifold, in this paper we argue that this theory always flows to non-trivial and to CFT, and there's although it could be possible this theory has experienced non-trivial Suji enhancement to n equal 4, but generally we don't expect to get any QFT. It doesn't have any mass gap. So in this case, closed hyperbolic manifold, it is very unlikely that we will get some QFTs from this hyperbolic manifold. When this manifold is non-hyperbolic manifold, which is given by this tensor representation, given by 3 co-primes, and then we found that this corresponding theory always flow to the unitary QFT or has Suji enhancement and CFT. So in these cases, we can always assign some rational VOA associated with this three manifold. And so this IR dynamics analysis is very non-trivial. So for example, so we are considering this three manifold, which is obtained by tensor of the integer tensor of the 5 to naught. And the corresponding field shear description is given by this one. And we can analyze this IR case using localization, very non-trivial step. Then we found that for P equal 1 and 2 cases, this theory experience very non-trivial supersymmetric enhancement and flow to length zero CFT. And when the P is in this range, then this theory doesn't have any new less gap generation doesn't happen, and the supersymmetric enhancement doesn't happen, and just flow to n equal to CFT. And actually, this is actually in a good agreement with that the topological fact that if we pilot to not, then P surgery, we know that in this case, we know that this three manifold is given by the hyperbolic manifold, given by this one. And in this case, it is known that this is all hyperbolic. So this is compatible with this IR case. So, and in this way, we can also analyze the 2 and 3 type, which is studied by this Target's paper. And we found that from the field shear analysis, this theory will flow to the has mass gap, unitary theory, and has a flow to the G2 and Chunsan level shield. And this will explain why that we get a vacuum character of G2 Chunsan level assuming with the model from this paper. Because that this theory have given by G2 Chunsan level, Chunsan theory, and under suitable boundary condition, this will support this G2 Chunsan level 1 assuming with the model, and they get this result.
So in this example, how do you see the modular weight?
Yeah. So that's we should rely on the localization. So we can compute the 3-square partition function and the length
Yeah,
space
but
partition function.
the derive is one another, but if you have some of the figure in one, but no, it's like a 3 halves.
These 3 halves?
Can you derive the modular weight?
Yeah, that's I don't know. That I don't know. Yeah.
I see.
So the procedure from the WRT to this model function is distance to me. So and just adding some data function, yeah, does not change the theory. Yeah. So every step is the but yeah, just including some data function, then we can make it always make the modular 0, and then this can compare with the vacuum character of the yeah. I don't know why they get a modular weight and but and then I'm now finishing, and then naturally we can generalize to that for Torus dot cases. In that cases, the Hikami mentioned that this associated Kasai invariant is related to the vacuum character of Virasoro minimal model. So we expect that this corresponding solidity theory will have a topological field theory whose topological field theory structure is same as the topological structure of the Virasoro minimal model. So yeah, the main result is that it works, is the conclusion. And by checking each cases one by one, we don't know how to generalize general cases. We have verified that. So we are considering knot complement, P gain knot complement, the Torus knot complement, which is labeled in P and Q. And we do the analyzing, we know the explicit field theory construction using the ideal triangulation of the Torus knot. And then the localization, we can analyze the IR dynamics. And then it turns out that we found that when the P and Q difference is 1, then this theory has always a mass gap, standard mass gap in non-trivial and have a mass gap and the flow to the unitary cavities. And when the P and Q difference is bigger than 1, and we found that this theory always has a supersymmetric enhancement and flow to length 0 CFT. Then, so since this one, then we can define the TQFT labeled by PAQ. For unitary cases, this is just the IR TQFT of this one. And in these cases, this is topological twist theory of this length 0 CFT. Then we can check that case by cases that this modular tensor category structure of these TQFTs are equivalent to the modular tensor category structure of the Virasoro minimal model. So if there is always a rational Boyer, there is always associated topological information, which is called the modular tensor category structure, and they are agree. So of course, we cannot check that every element of the modular tensor category structure. We can check that at the level of the modular data of the localization computation. And recall that this Virasoro minimal model is known to be unitary for these cases and non-unitary in this case. So this is compatible with our expectation. So we check the case by cases, and please believe this result. And when we give a very concrete example, this is my almost last slide. And we are considering the simplest non-unitary Virasoro minimal model, which is 5-2 knot, and the corresponding Torus knot is given with this one. Then this Torus knot is known to can be identically triangular by the 3 tetrahedra. So, and I don't know how to draw this 3 tetrahedra gluing, but there's very nice mathematical some computer software called Snappy. Then if you ask for the gluing equation, then they agree with the gluing matrix, Neumann-Jaquet matrices. This 5-1 knot denotes the 5-2 knot, Torus knot in the Snappy notation. And then they give this Neumann-Jaquet matrices. And using these matrices, doing some trivial manipulation, and we get a Neumann-Jaquet matrix A and B. And then we obtain the K matrices. And then using this K matrix, we can construct the 3D n equal to K theory. which is by the U1 to the K, U1 to the cubic with the Chern level, this one, decoupled 3 chiral with the spoof data. Then we can do the field theory localization analysis, and we found that and we can check that this theory is actually IR dual to the T minimum theory, which is checked in this paper. And recall that this T minimum theory support boundary algebra, which is Virasoro, the Liang model. Liang model is actually the same as this Virasoro minimum model M2, 5. So this is compatible. And then using this field theory description, we can construct the half index using this K matrices, which is obtained by Neumann-Jaeger matrices. And this factor also can be determined from the field theory analysis. Then we found that this reproduces the Virasoro vacuum character of the Virasoro minimum model. So this will give there's a vacuum character is of course very well known, but this expression is totally new, I guess. Yeah. So in this way, we can give many new NAMSOM-like formula for vacuum characters of this Virasoro minimum model using Neumann-Jaeger matrix of this not complement. So yeah.
Maybe it's also from the 3 manifold.
Yeah. Doing data, you can determine it. Everything is determined and everything. So I'm only showing this example. There are many other interesting examples until and check that these always work, and we can also check that we can also reproduce the characters of this theory from the field theory analysis. So let me summarize. So this is a conclusion. So this is I explained the 3D correspondence, which is relating 3 manifold to 3D n equals K theory, and I also explained the recent development, which is assigning some modular tensor category and the rational Broglie or its characters from the 3D n equals to K theory. Certain right choice of 3D n equals to K theory, and combine this one, we can assign a 3 manifold to this rational Broglie. And the one nice example is that the Torus knot cases, then it will give the Virasoro minimum model. It's nice that there's all labeled by P and Q, and they are all the same. And this can be generalized to in four directions. And we can also replace the 2 and pi brane to n and pi branes. And then in this case, we expect that this Virasoro minimum model is replaced by Dublian minimum model, which also labeled P and Q. And more interesting, we can also generalize the Torus knot in the arbitrary knot and link complement. Then in this case, we can also expect that the resulting 3D theory is either having mass gap or has switchiness to rank 0 theory and has a topological field theory. So yeah, so you can just do the field theory analysis. You type non-hypermorphic manifold on the snappy and get a limitation, then construct the K matrices and do the field theory analysis. Then compute the half index, and we will get some characters, and we can identify which RCFT will give this character, and we can identify. And this way, we hope that we can give some new RCFT or non-RCFT. And another interesting direction I'm considering in these days is that so we can also consider some domain words between the minimum models in 2D, or also it's a Burke dual, which is domain word between the rank 0 CFTs, or some topological field theories. And in 3D field theory sense, we are considering domain word, two-dimensional domain word, which is separating two different Virasoro minimum model, which is labeled by the P and Q and Q and Q. And in terms of 3D correspondence, this geometry domain word will correspond to cobordism between the two knots, Torus knot. Although this is not drawn the Torus knot, we can consider cobordism between the two knots. And recently, I found that many mathematicians already studied this kind of the cobordism between the Torus knot. And then I'm trying to connect this cobordism construction to domain word construction of this minimal models. And maybe I hope that I can say something interesting along this. Thank you.
Thank you, Dongmin, for the very interesting talk. Any questions? Yeah.
On top of characters, is there a way to directly capture the vertex on the structure by computing the local,
Yeah.
constructing local
Yeah,
and the
yeah.
local beams?
Yeah, so when the 3D theory doesn't have it, so the problem is that in 3D theory contains lots of the potential which is given by monochrome operators. If there's no monochrome operators, in principle, people have developed tools to analyze the rational VOA. So for example, so in a team model, there's no scope potential. In that cases, we can actually reconstruct some Virasoro minimal Virasoro small pi vortex operator developed from field theory. So generally, but they has some monochrome operator deformation. In that cases, the analyzing this boundary vortex operator is very tricky and it's open case. Yeah.
Another question is, can you comment on the Orient equals to point of view? Orient equals to a four field here, where similar minimum models can transfer.
Yeah, that are directed upon a dimension reduction, twist dimension reduction. And the people recently found that so for the angle theory, and there is associated VOA, and some cases, I think theoretical cases, it is meant that this theory allow to this VOA become the rational, especially Virasoro minimal model. The simplest example is the minimal H0 theory, and the relation is recently understood in the sense that we are considering the H0 minimum, the adjust reduction, and then we are considering dimensional reduction along the S1 with some U1R topper twist, U1R twist. Then after dimensional reduction, in the theory has no fixed branch, but only from branches. From branch is lifted, and we will get a length zero theory, and the people recently analyzed that theory, and it is known to be dual to the T minimum theory. So in that way, it is connected.
Yeah.
Je ne sais more about how much control you have on the lines along the algae flow and relatively can compute the non-vector characters.
Yeah. That's a very non-trivial, and we can be done in the case by case study. So we don't know which UV case theory has a lot of the Wilson loop and lots of vortex loop, and it is apparently difficult to determine which one becomes the simple object. And in recent paper, in the last paper with here last years, we give some concrete criteria which will become a simple object. We give some criteria, something like that we are computing as times S1 on the insertion of this simple object should be trivial, zero, and the north pole and south pole becomes 1, something like this criterion. If we satisfy that criterion, we can claim that this is a simple object. But finding this Wilson loop satisfying that criteria is not trivial task.
With the UV, they can look like enough Wilson loop. So
Yeah. So
is it even clear that the Wilson loops are not logical? So is it clear if you understand why they become logical lines?
That's also that's become the topological after RG and after topology. So I don't know, the mechanism is complicated, but anyway, so we can UV gauge theory just simply by the U1 to the gauge theory, then we can try all the charges, U1 gauge charges, and then always can find most cases we can find all the simple objects on this scanning this UV object. Yeah.
So you get these characters from this tetrahedral decomposition of Riemann-Eaton.
Yeah.
But there are different ways of making this decomposition. There are these factor moves.
Mm-hmm.
So if you choose different decomposition, wouldn't you get some other expression?
Yeah, some other expression, but they should be same because they are the related by the.
You get another lump sum also?
Yeah, another lump sum, I guess. Yeah. So another lump sum, and because they are all related by the duality, and we know the half index is invariant of the duality, and for that, so we should also know the proper transformation rule of the boundary condition. Yeah, and different to 3 move will give a different to 3D gauge theory in the IR related by the simple duality. known anicotutability. So under this known anicotutability, people haven't studied. People studied how that the boundary condition should be mapped, and then under this boundary condition map, and they check that top index should be same. Yeah.
Last question. So for 3 and for 4, there are 2 Torus characteristics, A and Q.
Yeah.
For Torus not case, I think one of them gives you the minimum.
Yeah.
What about the other? Did you identify?
No, we haven't identified. So we now have field show it, and we can analyze the fit twisting, and we can get some overall data, something like that. But we haven't analyzed that.
Okay. Let's thank Dongmin again for the wonderful